Hello, I'm Shaumik, and I'll be presenting our work, ShuffleUNet, Super Resolution of Diffusion-weighted MRIs using Deep Learning. Diffusion-weighted imaging, or DW-MRI, is a method of signal contrast generation based on the differences in the Brownian motion. With the help of this, it is possible to evaluate the molecular function and microstructure of the human body. DW-MRI signal contrast can be quantified using apparent diffusion coefficient, or ADC maps, and it can act as a tool for treatment response evaluation and assessment of disease progression. Ability to detect and quantify the anisotropy of diffusion leads to a new imaging paradigm called diffusion tensor imaging, or DTI. DTI is a tool for assessment of the organs with highly organized fiber structures. Here is an example of DTI matrix: fractional anisotropy, or FA, mean diffusivity, or MD, radial diffusivity, or RD, and axial diffusivity, or AD. DTI captures the directional movement of water molecules along neural pathways. DTI is the only imaging method that shows the actual nerve tract instead of the fat surrounding nerve linings. DTI is useful for analysis of white matter, especially for detecting diffuse axonal injury and traumatic brain injury. Pathologies, those are not visible on standard MRI scans. Magnetic resonance imaging, or MRI, can provide high spatial resolution, excellent soft tissue contrast, without using harmful ionizing radiation. But MRI has a big disadvantage in terms of acquisition speed. Higher resolution images require longer scan time. For clinical acquisitions, there is usually a fixed amount of time per patient, and this can have an impact on the image resolution, on the image quality. This work aims to super-resolve low-resolution diffusion-weighted images. In recent years, UNet model has been widely used for various segmentation and inverse problems. It was originally proposed in 2015 for segmentation of neuronal structures in electron microscopic stack. Roughly, a unit can be divided into three parts. First is the contraction path, which includes convolution and max pool layers. Then is the latent space, and finally is the expansion path, which includes up-convolution and convolution layers, along with skip connections coming from the contraction path. Even though it is one of the most popular network architecture, it has certain problems. First is the max pool operation, which is used in the contraction path for downsampling. It chooses the maximum value in a given kernel, causing a loss of pixel information. Lossless pooling layer, proposed by Totunki et al., has been seen to perform better than max pool. The next possible problem is with the batch normalization layer, which can negatively impact the results as it restricts the range flexibility of the network by normalizing the features. This can also increase the GPU memory requirements by around 40%. And finally is the up-convolution operation, which can produce checker-box artifacts while upsampling a low-resolution data. Subpixel convolution instead of up-convolution can be a possible candidate to solve such problems. Lossless pooling layer, referred here as pixel unshuffle, reduces the spatial dimensions while increasing the number of channels by rearranging all the elements of the tensor. In this manner, the pixel elements are not lost but preserved as different channels. Subpixel convolution, also known as pixel shuffle, does the inverse operation of pixel unshuffle. It increases the spatial dimensions while reducing the number of channels by rearranging all the elements of the tensor. This helps to prevent checkerbox and other artifacts or blurring effects, as there is no interpolation involved from low to high resolution. Rather, all the pixel elements are already present in the tensor. They are just rearranged from channel to spatial dimension. We propose the ShuffleUNet architecture, which aims to solve the earlier mentioned problems of UNet. This architecture is based on tight frame UNet architecture. We have used pixel unshuffle and pixel shuffle in place of max pool and up convolution respectively. We also did not use the batch normalization layer. Now let's have a closer look at the different parts of ShuffleUNet. First is the contraction path, which condenses the supplied data into a latent representation. This path contains 4 contraction blocks. Each of the blocks contain a double convolution, a set of convolutional decomposition operations, and finally a pixel unshuffle layer. Next, in the ShuffleUNet architecture, we have the latent space. And finally, after the latent space, there is the expansion path. This path brings back the original input size from the latent representation. Expansion path contains 4 blocks. Each block contains a pixel shuffle layer, a set of convolutional decomposition operations, and finally a double convolution. The network starts with 64 as the initial number of filters, which is then doubled by each of the contraction path blocks and reduced by half by each of the expansion path blocks. It is also noteworthy that both pixel shuffle and pixel unshuffle operators have learnable parameters. And as a final note, the initial weights of all the convolution, pixel shuffle and pixel unshuffle layers are initialized using k-mean normal. To evaluate this approach, we have used the diffusion-weighted images from the EUSIPCO dataset, which contains 16 diffusion directions for 399 healthy subjects, acquired using 1.5 and 3 Tesla MRIs. This dataset was randomly divided into training, testing, and validation sets comprising of 350 and 49 subjects respectively. The original resolution of the images present in the dataset were 1.75 mm in plane and 2.35 or 2 mm in the slice direction. Undersampled dataset was artificially simulated by downsampling with a factor of 2 in all dimensions, taking the center of the k-space using FSL. The resultant downsampled volumes had a resolution of 3.5 mm in plane and 4.7 or 4.0 in the slice direction. As unit-like models require same matrix size for both input and output, the undersampled images were interpolated using sync interpolation, which is basically zero padding the k-space before supplying them to the network. And also, intensity normalization was performed as an additional pre-processing step after interpolation and before supplying the data to the network. In our experiments, we used a path size of 96 × 96 in plane and 48 in the slice direction. Patching was performed using torch.io. We trained the model with a batch size of 4. Loss was calculated using mean absolute error and was optimized using the Adam optimizer with a learning rate of 10 to the power of -4 for 80 epochs. The implementation was done using PyTorch and was trained using NVIDIA V100 GPUs. Now let's have a look at a result. It can be observed that the model could improve the input of undersampled MRI significantly, resulting in super resolved image close to the fully sampled ground truth. While looking at the results quantitatively using 3 matrices, structural similarity index, root mean squared error, and universal quality index, the proposed ShuffleUNet model performed significantly better than the interpolation techniques as well as than the UNet model. It is to be noted that these comparisons were done by considering each direction as separate 3D volume. But with diffusion-weighted imaging, we are more concerned about the different derived data: axial diffusivity, mean diffusivity, fractional anisotropy, and the diffusion tensors. Here's an example for qualitative comparison. It can be observed that the results of UNet and ShuffleUNet are closer to the ground truth than the undersampled input as well as the interpolated results. We also compared quantitatively the derived data obtained from the various methods against the derived data obtained from the ground truth using the universal quality index and the root mean square error. It can be observed that the ShuffleUNet performed better than the UNet model or the interpolation methods for all the different types of derived data. The derived data can then be used to generate 3D visualization of the fibre tracts. Here's an example of the generated fibre tracts from an output of ShuffleUNet. Now to conclude, Here we have presented ShuffleUNet, which is a modified tight frame unit architecture, which has been created by incorporating pixel shuffle and pixel unshuffle operations, and which also ignores batch normalization layers to deal with the drawbacks of unit-based processing pipelines. We have shown a patch-based single-image super resolution of diffusion-weighted MRIs using this network for an acceleration factor of 8. The network managed to achieve statistically significant improvements over the unit model as well as the different interpolation techniques. By comparing the derived data, we can conclude that the fiber tracts can be derived from the super resolved images similar to the ground truth images. Thank you so much for your attention, and feel free to contact me for any questions or feedback.